So for the next 45 minutes or so, I'm going to be telling you a story about data, because I think that's cool. And because I think it's cool, I'm actually, here's a promise/threat, I'm going to invite you to help me with this at a few different points along the way. See, after all this training in statistics and things like that, I wound up at MD Anderson, at the Cancer Center. And over at MD Anderson, I was a professor in the Department of Bioinformatics and Computational Biology for about 20 years. And these days, I would probably have other fancy titles such as expert in data science and machine learning and other buzz phrases that would make it more likely I'd get funded and things like that. But what this meant for me was really that people would bring me data. Lots of data, and it was high-dimensional data when high-dimensional was cool. And what this meant is that we got involved when people were just starting to generate assays, like microarrays and proteomics and sequencing stuff, where they could give us not just measurements on one gene or two genes, no. We could get thousands of measurements all at once for every single sample, and they'd bring the data to us. And the clinicians would say, find us a pattern. Find us something that we can use to change the story, to change what we're doing, to change and make things better. And we said that would be great. We'd love to do this. And we got really excited because there's all these patterns out there, and you can find them. And there's, however, a problem, which is that for many of these patterns, they involve combining not just one gene again, but 50 or 60 or 100 or things like that. And the problem is that our intuition about whether a pattern makes sense in 50 or 100 dimensions, our intuition sucks. That's mine, that's yours, whatever. And I know this because one of the things that we've seen with gene lists and things like this is, for example, we've taken gene lists of 100 genes to some cancer oncologists we've worked with, and we said, we've based a pattern on this, and based on this, if the score goes up, the patients do worse. And the doctor will take this list and will say, yeah, well, I can see that because this interacts with this, and this interacts with this, and they'll construct a story right in front of our very eyes, and it's almost like a Rorschach test. And the scary thing for us is that from time to time, on accident, we've given them incorrect lists of genes. And they still say, yeah, this interacts with this interacts with this, and they will still construct a story right in front of our very eyes because our intuition sucks. But that presents us with a challenge because we got into this because we're really excited about the potential. We want to believe that we can use these patterns to improve patient care. But if we can't trust our intuition about them, that means that we have to be able to trust the process by which those were assembled and be able to check those steps so that we can confirm things that we can validate in a simpler fashion. So that's really cool. And that's what we've been trying to do for a good long time. Occasionally, as part of this, to augment things, we will go out and we will help read the literature. And we will read the literature, we'll read these high-profile papers in obscure journals like CNS. And then people will say, oh, we'd like to build on this. And we say, sure, we'll help you build on this. Let's just check the quantitative results from this paper, and once we confirm that, we'll move on. That should be fast, because they published the methods, they published the data. It should be easy. Now, I don't know how many of you have tried this particular experiment of taking a paper and taking the published data, not trying to do any wet lab experiments, just trying to reproduce the quantitative numbers from the numbers they've posted, and seeing, is this quick and easy to do? It is not, on average. And what that means, a lot of the time, is we say, okay, it's not filed appropriately. But occasionally, we are presented with an additional challenge, which is people come back and say, no, we really care about this result. We really want to know how they did it. And we can't figure it out. And that has led us to develop an entire new subfield, which we got to name because it was work group, and we called it forensic bioinformatics. And what this subfield does is it is the art of saying, okay, what are the results they obtained? What's the data they started from? can we figure out what the hell they must have done to get from here to here, regardless of what the methods say they did? And this is occasionally informative in ways you might not expect. But it's useful, and it does come up because some of the questions really are important. Here's the question that's actually going to motivate the rest of my talk, which is, can we predict which patients will respond to which drugs? This is important. If a woman shows up at MD Anderson with advanced ovarian cancer, we will generally give her standard frontline therapy, which will involve a platinum agent and a taxane. We do this because we know that for roughly 75% of the women we treat this way, it's going to help them in the sense that it will reduce their tumor burden, it will extend their life, it will hopefully improve their quality of life longer term. But in doing so, we also know that there's 25% of these women that we will poison to no good effect for 6 to 8 weeks, but we do it because we don't know which ones they are going in. If we knew which ones it wouldn't help, we'd do something different. And it is in light of this that a few years ago, people at MD Anderson got very excited because a paper had appeared in Nature Medicine where the authors had claimed to have a pretty good approach or answer to this type of question. And in particular, one of the things that they did is they said, we've been able to use a new high-throughput assay, microarrays, and use gene expression patterns to come up with predictors of drug response. So how did they do it? Well, they said, well, we're going to build you a tool, and we're going to use all publicly available data to do this. And in this particular case, what they did is they started with microarray profiles, not just of patient tumors, but rather with microarray profiles of cancer cell lines. And in particular, they started with a really special panel that has been maintained by the National Cancer Institute, the NCI, and this panel of cell lines is known as the NCI 60. The NCI has maintained this for 40 or 50 years. What's special about this panel? Well, for our purposes, the main thing that's special about this panel is that every time a new chemotherapeutic is introduced into practice, and sometimes even before, the NCI will officially assay how effective this drug is against every one of the cell lines, how much of the drug is required to cut the growth rate in half. And that sensitivity data is publicly available. That's publicly available data for every drug we use today. So if we could somehow say, based on the pattern of expression of these cell lines, we can predict which cell lines this drug will be useful for, and we can extrapolate from that to which patients it will be useful for, that could, in a sense, provide a Rosetta Stone for a whole bunch of stuff that we want to do. And they said, we think we know how to do this. So let's take these cell lines, and let's take a drug of interest. Let's say it's docetaxel. We'll take a look at the sensitivity data, and we'll use those to order the cell lines. And then we'll take the most extreme cell lines, let's say 7 at each end, and we will look at the microarray profiles of those extreme cell lines. And then, gene by gene, we will compare the expression levels using immensely sophisticated statistics like 2-sample t-tests. And we will identify the 50 genes that are most different. And we will say the pattern of expression in those 50 genes, that comprises the signature of sensitivity to docetaxel. And then what we will do is we will take a microarray profile of a patient sample. We will look specifically at the expression of those 50 genes, and we will say, does the pattern of patient expression look more like the sensitive profile, in which case we'll treat them with docetaxel, or more like the resistant profile, in which case we'll try something else. Sounds moderately straightforward in concept, and the reason they got to publish in Nature Medicine about this is that they said, we've now tried this, trying to predict response to 7 widely used agents using publicly available data on patient samples and on cell lines, and we get great results every single time. Within weeks of this paper appearing, we had groups from several different clinical groups at MD Anderson, several different organ sites, coming to us in bioinformatics saying, we want to do this. We want to treat our patients better. We want to use this method, but this method involves math, which is scary. So we need help. And we said, okay, great. We think we can help you with it. And because the data is all public, we said, sure, let's just check it. Let's make sure we can do it, and let's move on. And we decided to as a first step, do something we thought should be easy, which is, let's say, take one of these drugs that they looked at, and then say, if we look at the same cell lines and we try to identify the genes, can we come up with a roughly corresponding list? Now, one of the reasons we thought this should be easy is that one of these supplementary reports attached to this paper was, for this drug, here's the list of the genes we found. For this drug, here's the list. And there's further discussion in the paper about why these lists make sense. So we looked at them and we said, okay, I'm a PhD level statistician. I can do a 2-sample t-test. I can do lots of them. I can do it very well. So we took the samples and we looked at 5-fluorouracil. That's one of the drugs they use. Great, okay. They identified their top 45. We said, okay. Went in, we ranked this up. We identified our top 45. And the overlap between their top 45 and our top 45 was 0. And we said, that's probably not good. So we said, what the hell's going on? So we started looking more closely at the genes they were using. And here we get to an issue which is not technically biology related. It's more an issue of indexing, which is that when you start dealing with not just 1 or 2 or 5 genes, but hundreds or thousands, you tend not to refer all to them by name anymore, because that's sort of useless. You just refer to some type of index. And in particular, the genes, the arrays they were using were manufactured by Affymetrix, a company that made the microarrays at the time. And the way they were looking up the genes was they were using Affymetrix probe ID. Now, why does this show up as important? Well, here on this list are the probe set IDs for the first 4 genes that they identified as being important for predicting 5-fluorouracil response. Here are the first 4 that we identified using 2-sample t-tests. If you go from their list to ours, does anybody see a pattern here? We have an off by 1 index in here. What's going on? Well, we tracked down the software that they were using to come up with their lists. I wrote the comments for it because none existed before. In working through their software, it turns out that their software requires 2 inputs. The first is a list of gene expression values with a header indicating if the sample is sensitive or resistant to treatment, and the rows indicating the genes, and that's what you get. And there's a second input, which is a list of gene names to say, what are these genes? And it has to be in the same order. But the expression value had to have a header row saying sensitive or resistant. For their software to work correctly, the list of gene names must not have a header row. So if you're working in Excel and you cut and you paste, and you leave on a header row, guess what happens? You get an off by 1 indexing error, which means that they published a story about these genes which are actually uninvolved in the biology. And this is the case for every one of the 7 drugs they looked at. And it is the case that they found a story which they expressed in words in the paper for many of these signatures saying why this makes sense. It's got by the authors, it's got by the reviewers, it's got by the editors, because our intuition in hundreds of dimensions sucks. So we said, okay, that's a problem. But it isn't actually necessarily a fatal problem, because what we really care about is, can we use the gene expression values to predict patient response? The list of which particular genes were involved in their names, that was tacking things on at the end of the day. If the numerical patterns still let us separate sensitive patients from resistant patients, that's still good enough. We can still work with that. So we said, okay, let's try to do it ourselves. Let's take the numbers and let's see if we can predict patient response. So we want to say that we can do it really well, and we'll think we understand the method if we can do a good job. But that led to our having to define a good job. So we said, we'll say that we understand it well enough to use it if we can get results as good as the ones they reported. And that was good enough to get them published in Nature Medicine, so okay, fine. So how good were their results? So in this top panel, I am showing their accuracy in predicting patient response to treatment with single-agent docetaxel. This is a patient of women with breast cancer. The blue squares indicate patients who were sensitive to treatment. They mostly had low scores. That's good. Patients who were resistant to treatment, red triangles, mostly had high scores. That's good. So low and high separate pretty well. So they didn't get it perfect, but the accuracy was above 90%. So they said, okay, that looks pretty good. But I mentioned early on that all the data that they were working with was public. So we'll come back to this, because this is actually going to be important. But here's another thing that I warned you about, which is that I'm going to ask for help. So here I need some help with a statistical question as we're looking at accuracy. Specifically, as we look at these ones where they got 90% right, how many sensitive patients are they talking about here? How many blue squares are there in this figure?
13.
Thank you. There are 13 blue squares and 11 red triangles. 13 sensitive, 11 resistant. Now, we went back to the source paper from which they got these samples. This was a paper published by Jenny Chang's group. Jenny's over at Baylor, dealing with patient cancer. And they spent a lot of time in their paper talking about their 11 sensitive and 13 resistant patients. Not 13 and 11, but 11 and 13. And we said that might be an issue. So we decided to take a look at another drug. And for those of you who are overly ambitious, how many red triangles are there? For those of you who aren't going to go, yeah, you'll probably be willing to grant me that there's more red triangles than blue squares. This is for another drug, specifically adriamycin, where they said we predicted with great accuracy. Problem. The paper from which these data came was in the New England Journal, and it was dealing with the prediction of response to childhood ALL. Now, as tumors go, this is actually one of the ones we know how to treat. We've got a cure rate above 80% with this thing. But that leads to a different question, which is that if we've got a patient population with that high a response rate, and we've got a drug to which that high fraction are resistant to treatment, we wouldn't be using that drug, ever. And indeed, the publishers of the New England Journal paper thought that most of the patients were sensitive, not resistant. So what's going on? Well, I glossed over a bit earlier. I said that when they used this expression matrix, they had a header row indicating sensitive or resistant. Well, what they actually supplied was a matrix where they used at the top row either 0 or 1, but they never explicitly wrote down 0 equals sensitive, 1 equals resistant. So in some cases, from going from one drug to the other, they got the interpretations reversed. So what would this mean? It would mean that if you were to take their method, and their method works, and you were to apply it clinically, they would recommend administering adriamycin only to the patients who are most resistant to treatment with it. This is poor clinical practice. We do not advocate this. We think this is a bad idea. Now, this bit, or this various discussion that I have gone through with you, is not something that it took us 10 or 15 minutes to work out. Now, this was about 6 months of back and forth with the authors saying, we're trying to do this because we'd really love to use your method. By the way, we don't fully understand it. By the way, your gene lists appear to be off. By the way, can you help us with these sensitive resistant things? And eventually there was this, by the way, when we try the method ourselves, using the labels we think are correct, we can't get it to work. Where are we getting things wrong? Here's our code. And what this resulted in, at the end of this several months of interaction, was that the authors got back to us and said, well, obviously this interaction has ceased to be productive, so we wish to draw it to a close. And we said, okay. So we drew it to a close. We wrote up our various findings, and we submitted this as a note to Nature Medicine. All 700 words of our note that they would let us have. And 130 pages of supplementary reports and things like that, with all our code. And then we waited to see what would happen, when it would be published. And that November, it got published in Nature Medicine. And one of the things that had us excited about this was that when you publish a critique of somebody's paper in a journal, the authors are typically given the right to respond. And we were curious as to what the response was going to be. Were they going to say, oh, we're so sorry, we screwed it up, we'll never do it again? And well, that wasn't precisely the tone of the response. The response was that, unfortunately, the analyses by Drs. Baggerly and Coombs are deeply flawed. They have not followed our methods. We have gone back and checked our data. Our labels are correct for our adriamycin data. That's the one with all the red triangles. Nope. We're sure that we're right there. And furthermore, since our initial publication, we have continued to apply our approach to make further predictions in other high-profile studies and gotten great results again. So we continue to have other high-profile publications, so we must be right and they must be wrong. Huh. Now, I remember this. I remember the evening I read this very clearly because I wasn't here in Houston. I was in Bethesda, Maryland, because I was scheduled to give a talk at the NCI the next day about all of this. And I was finding out the night before I actually gave this talk that, oh, by the way, everything I was about to speak about was wrong. This didn't cheer me up. So I said, okay, they said they got the labels right, they posted the data, let's take a look. So I downloaded a big file of data for adriamycin. Big Excel table, 144 columns, with header rows saying, is this sample sensitive or resistant? And another header row saying, is it a cell line for training or a patient sample? Okay, fine. Then genes, thousands of rows, something like that. First thing I did, counted the number of resistant, responders, non-responders in the patients, and they got non-responders, and they add up to the number of red triangles. Maybe we screwed up. Maybe there's a pattern in the data I can exploit that can at least tell me something. So I took all these columns of data, and I said, I want to check how close these are. Maybe I can find some clusters. So I said, let's check the correlation between every pair of samples we got here. And this is what I got. This is a plot showing the correlation between every pair of samples where the correlations are really high, almost perfect. These are the cell lines. This line of red dots says that cell lines are highly correlated with themselves. I believe that. That's good. Okay? These are patient samples. This line I expect. These I didn't. What's going on there? Well, they have 122 columns that they say are from patient samples. That may be true, but the 122 columns are not all distinct. Some vectors of numbers have been reused 2, 3, or even 4 times. It's not different patients, it's the same one. And right about here is the data for one patient that was looked at 4 times, where that one patient was labeled resistant 3 times out of 4. So we're pretty sure they don't have the labels right yet. And we sent this as a note off to Nature Medicine. Nature Medicine said, oh, well, the authors will make a correction. There's no need to publish your objection. And the authors came back a year later and said, oh, well, we've redone the analysis using only the 95 unique samples, and we still get great results. The problem was that when we counted the number of unique samples, we didn't get as many as 95, so this was a surprise to us. And when we looked at the data they posted this time, only 80 are distinct, 15 are used twice, and of the 15 used twice, 6 are labeled both sensitive and resistant, so they still haven't got the labels right in a correction. So the correction of a correction still needs correcting, but Nature Medicine had said it was done, so we moved on. We moved on because they said they used other high-profile studies to confirm this. So we said, let's look. So here's another of those high-profile studies. Journal of Clinical Oncology is extending the approach to deal with 2 new drugs, cisplatin and pemetrexed, often used in the treatment of lung cancer. So we said, great. What does this, do we believe it? Well, they said, well, you should believe it because when we use these arrays, when we check the gene list for cisplatin included ERCC1, ERCC4, and several DNA repair genes, and we know that's how cisplatin works because there has just been several recent papers in the New England Journal saying, here's how this works. So we said, okay, let's get down to it. So we took their heat maps, and we took their gene list, and with some work, we were able to match their gene list mostly. For pemetrexed, they reported 80 genes. We can perfectly match their list of 80 genes after we account for the off-by-1 indexing error, which they're still making. Then we went to cisplatin. For cisplatin, they reported 45 genes. After accounting for the off-by-1 indexing error, we can perfectly match 41. There's a difference, isn't there? How many? Four, yes. So what are the identities of the 4 that we can't match? They are probe sets corresponding to ERCC1, ERCC4, ERCC1, and a DNA repair gene. These are the ones they mentioned as explaining why this should make sense. So these we can't match. The numbers don't generate them. Even better, these last two are actually really special, even in this context. Why are they special? Well, it's because they're special because at this time of the game, miniaturization wasn't as advanced. So Affymetrix couldn't fit all the genes in the human genome onto one array. They still did as a 2-array set, but they posed most of the known genes on just the first of these. So most people would just run half the arrays and they'd be done. Well, that's what they did, but it turns out that these last two probe sets, two of their best ones, are on the arrays that they never ran. So that's a neat trick. So we sent a note about this off to Journal of Clinical Oncology. And JCO got back to us and said, we're sorry, we can't publish this. We sent them a second note saying, can you tell us why? They sent us a second note saying, we're sorry, we can't publish this. So we moved on. Here's the other paper that was high profile that they said was validating their approach. See, it's right there in the title. Validation of gene signatures. That's the entitlement. This was in Lancet Oncology. What they did here was they extended the approach this time, not to dealing with just one drug, but with dealing with how their method could be extended to make predictions for responses to combination chemotherapy. This is really important because we typically don't treat cancer patients with just one drug. We try to hit the tumor several different ways in the hopes that something will work. And so they said, well, same approach, but here we're considering two combinations. One combination is 3 drugs, fluorouracil, epiuracil, and cyclophosphamide. The combination is known as FET. The other combination is taxotere, followed by a combination of epiuracil and taxotere. So that's known as TET. This is actually 2 drugs, because the T is actually taxotere in the same cases. So we have 2 combinations, and they said that we made predictions with both of these. And if we use their predictions, instead of allocating the patients at random to treatment arms, they claimed that we would have improved the response rate from 44% to 70%. That's a lot. So we said, okay, let's take a look at it. In particular, we downloaded the data and we said, let's take a look at clusters. Can we identify maybe 2 clusters, like responders and non-responders? So, how many clusters are there? Not a trick question. 3. Okay. So what explains why there are 3 clusters, not 2? Well, it turns out that if you spend time looking at these raw numbers and the raw data files, you learn something about these data files. And one of the fun things about these data files that you learn to look at real early is the top few rows. Because the top few rows don't contain gene expression values, they contain metadata like where was this experiment run, when was it run, and things like that. So over here on the right, I've plotted these same samples as a function of when they were run. This block corresponds to samples that were profiled on arrays in about January 05. Second block, up here. Third block, up here. Those clusters are run data. Second thing, if we look at what symbols I'm using, these symbols correspond to different types of treatment combinations. Black squares, black circles, those are patients treated with FET. Greens, those samples were omitted from the final analysis for one reason or another. So these first 2 include all of the black circles. That's all the patients treated with FET. That last one, red stars, that's all the patients treated with TET. So all the patients treated with FET and all the patients treated with TET were profiled on assays that were giving systematically different results because they were run months apart, and as it happens, in different countries. So there are some differences. They're just not clinically relevant. So that's one issue, and that's experiment number 9. But there was another issue that we were really curious about, and so anybody here a statistician, or a mathematician, or a computational biologist in training, things like that? Maybe 1 or 2? Oh, yes. Well, okay, then to everybody else, I apologize, because this is my slide with formulas, which is that specifically, I said that they figured out how to apply the approach to combination chemotherapies. And we were real curious about this because we sort of thought we understood what they were trying to do one drug at a time. But how did they put those numbers together? Well, we went back to their Nature Medicine paper, and in their Nature Medicine paper, they alluded to a hypothetical approach that they could use for predicting response to a 4-drug combo, TFAT. And then these others, so we said, let's track down what the rules are for the numbers. So we worked at it, and we came up. We were able to figure some things out. So this is the rule for the 4-drug combo. The probability that a patient will be responsive to this combination is the probability they will be responsive to this drug plus the probability they will respond to this drug, plus this probability, minus the product of all four. And now, since this person in the back was kind enough to identify herself as being, you see something wrong with this? See, I'll tell you that we thought that there was something wrong, and they thought that there was something wrong, because all the numbers they got with this formula were bigger than 1.
The probabilities of combinations that are not all 4?
Yeah. This is actually, it's a rule that works for 2 events. It's the rule for independence. They just generalized it wrong. But they knew that it should work, and they know that numbers bigger than 1 were wrong. So they said, well, we'll take the biggest one, we'll set it to 1, we'll take the smallest one, we'll set it to 0, and we'll linearly interpolate down from there. This step did not make it into the methods section. This step is something that we figured out because we tracked down the Excel file where they had all the quantitative results, and we said, oh, that's what they used. Well, okay, now I just told you that this is the 4-drug combo. Now for 2 drugs, one of the combos they used in the more recent paper, ET, that's just 2 drugs. So this rule should work there. So what's the rule they use there? This does give numbers between 0 and 1, but it's different. What about the 3-drug combo? I have a standing offer to buy dinner for the first person who can explain to me where the hell this rule comes from. I have no clue. But it's what they use. Now, there is this problem. And I'm going to paraphrase a rather famous American and tell you that as a bioinformatician, I have a dream. My dream is that if you are going to validate a predictive signature over time, that you would keep that signature the same. Not an unreasonable dream, but it didn't work. Okay. So is there anything else that we can use? Well, we thought maybe we can try something else. We don't believe they're combinations. We're worried about the design. But still, we at least know individual drugs. Maybe if we predict response just 1 drug at a time to extrapolate that to predictions for the combo, that might be useful. And indeed, the authors thought that this might be useful. So they said, if we try to predict things 1 drug at a time, the single best predictor is cytoxan. This is 1 drug. And this, if you want to predict response, here's our receiver ROC curve, and it's beautiful. For an ROC curve, you want it to be going up into that corner. This is almost perfect. This is beautiful. When we generated our ROC curve from the same data, this is what we got, so we were getting confused. But we also stared at this and we had a clinical question. So do I have any doctors in the audience? Any MDs? Anybody willing to self-identify as MD, knowing that I'm going to ask you a question? Somebody not identifying, but okay. So here's my question. What's a prodrug? So the metabolic response or something like that. So I'm going to translate this, and you get to nod and see if this is roughly correct. Which is the drug is, it's not something that is active in and of itself. It is processed by the body into its active form. Now, the reason this matters, cytoxan, or cyclophosphamide, is a prodrug. So my second follow-up question, which is, what do you think happens if you give a prodrug to a bunch of cell lines that don't have livers? Nothing happens. So how did they identify cell lines that were sensitive and resistant in the first place? Well, it turns out that we checked more closely, and these cell lines are indeed sensitive and resistant, but to pemetrexed, they got the drug wrong. But they got great results, so who cares? So we wrote up these various objections, and we sent this as a letter off to Lancet Oncology. Lancet Oncology wrote back to us saying, well, you appear to be objecting to differences in statistical methods to which, as everyone knows, there are no right or wrong answers.
Oh.
As a result, we do not see the need to publish your letter. So we said, okay, and we moved on. We moved on because there were some other folks dealing with glioblastoma, brain tumors, who came to us and said they're now talking about using this for temozolomide, which is a drug we use all the time. Here's the heat map, here's the paper in CCR. Can you check this? And we took the numbers, we said, can we match this heat map? And we said, we can't. Weeks of trying, we can't do it. So we decided, let's go back to the literature. Maybe there was something we missed. Then we looked more closely at the heat map that they reported for cisplatin a few years before. We didn't feel so bad anymore because We could match this with the data for cisplatin. It's not for temozolomide. So we sent a note to the editors of both these two journals saying, one of these is wrong. We will leave it up to you to figure out which one. We got a note back from the editor of CCR saying, oh, the authors submitted the wrong figure. It's no big deal. They'll submit a new figure. We'll just move on. No need to publish your objection. So they got back with a new figure and a new gene list, which didn't agree with each other or with the text of the paper. So in this paper, they had achieved the neat hat trick of having a heat map about one drug, a gene list for a second, and text describing a third. But then moved on. Now, there is this minor question, which is that, why do we care? So we've been doing this because people at MD Anderson have been asking us to gradually for 2 or 3 years at this point. And this is when some friends at the NCI called us and said, by the way, do you know these guys at Duke, which is where they were based, they're already using these in clinical trials. They are using these rules to decide which drugs patients get. And we said, no, we weren't aware of that. So we combined all of our various objections, we put them into a single paper. And the first thing we did was we sent it off to the editor of a rather prominent biological journal for informal comment. His feedback to us was that, well, your story's too negative. Can you fix that? And we said, you know, we really don't think we can. So what we did next was we submitted our paper to the Annals of Applied Statistics, because most of you guys read that journal too, right? And the response there was a bit different. I got an email from the editor of that journal that evening saying, I like this paper. I'm going to handle its review myself rather than handing off to an associate editor, which we took as a good sign. And 2 weeks later, we got another email from the editor saying, we've decided to accept the paper as is, no need for revisions. It's posted online now, which means I'm sending more papers there. But the other thing about this is that now that our paper is part of the published literature, we could cite it in, for example, discussions with the press. And indeed, a few weeks later, the Cancer Letter carried a story where it said, biostatisticians are alleging the potential for patient harm in clinical trials being run at Duke University. The horror. And unbeknownst to us, groups at the NCI read our paper, looked at grant applications from this group at Duke and said, we see the same problems here. The NCI wrote to Duke's Institutional Review Board. That's the group in charge of patient safety. They said, we are concerned about patient safety at your institution. Will you reassure us? Now, I'm a professor at a different institution. There's a limit to how loud I am. The NCI is giving them tens of millions of dollars per year. They pay attention. So, Duke said, you know what? We're going to pause enrollment in these clinical trials, and in the meantime, we will convene a panel of outside experts to look at the data and say, should we proceed? And we said, okay, we can live with this. We're not happy that clinical trials started, but given that they did, outside panel, we can live with that. And we said, will anything else happen? Well, actually something did, which is that while this review was supposed to be going underway, the authors posted brand new data to their website. And what new data was this? This was the data that they said, these are the validation data that we used for our signatures for cisplatin and pemetrexed. This is how we proved it worked. And here's what it is. Here's their subset from a larger data set, but it's here. And we said, cool, we can figure out how it works. So we downloaded the data. We looked at it. We said, what are the samples? And I tried this correlation trick, and what you should see in this plot, if the samples are what they say they are, is you should see 59 red squares, one per sample they used, all falling on top of this blue line. How many red squares are on top of that blue line? 0. As it happens, there's only 43 red squares in this plot at all. That means the red square says that we've identified this vector of numbers. We can perfectly match it. They got the name wrong. That sample isn't the one they think it is. And because they got the name wrong, they got the clinical annotation wrong. There's 16 samples where there aren't red squares at all. Why not? Because for those 16 samples, they've already scrambled the gene names so badly that these are no longer valid samples of anything.
Oh, good.
All 59 of their validation samples are wrong 2 years after they started clinical trials using these drugs. We wrote this up as a separate report, which we sent to the NCI and to the deans of Duke at Duke who were overseeing the investigation. And we waited to see what would happen. What happened was that about a month and a half later, Duke announced they were going to restart the clinical trials. Because their experts had concluded their investigation and their investigation's results had strengthened their confidence in this evolving approach to personalized cancer treatment. We were curious, so we said, would you show us the data supporting this decision? And Duke said no. While the reviewers approved of our sharing the report with the NCI, we consider it a confidential document. A future paper will explain our methods. We're going to explain why it works later, but we're going to treat the patients this way now. And that's frustrating. But Duke said something there. While the reviewers approved of our sharing the report with the NCI is a federal agency, which means that in this country, they are subject to the provisions of the Freedom of Information Act. So we didn't have to get the report from Duke. Indeed, when they told us this, we filed a FOIA request with the NCI. And a few months later, we got a copy of that report, and we looked through it, and we said, this doesn't justify restarting trials. We got a whole bunch of other biostatisticians to look at it and said, nope, doesn't. And we sent this off to Duke saying, why the hell is this going on? Duke had no comment. So there I was, objected how I could. I was really depressed, sitting in my office. And I got a phone call. The guy said, hi, I'm a lawyer. You've been making objections about this group at Duke. I have a client who thinks there's a few things you should know. I talked with him for a bit over an hour. I said, that's really interesting. Here is the phone number of a reporter I think you should talk with. And about 2 hours later, I got a call back from Paul Goldberg of the Cancer Center. And Paul said, I'm going to have fun. I was in a better mood at this point. So, why was Paul going to have fun? Well, a few weeks later, he got to publish a story where he pointed out that, oh, by the way, one of the Duke PIs used to claim on grant applications and his CV that he was a Rhodes Scholar. But the Rhodes Foundation didn't agree. Even better, he'd sent some questions to the author in question, asking him if he could explain to this. And the author, Anil Bodhi, said, well, maybe I should talk with him. After all, I was a nominee. And the fun thing here is that Paul had CC'd a bunch of Duke deans on this, and Bodhi hit reply to all. So what has just happened? A faculty member at Duke has just admitted in writing to a reporter, CCing all the Duke administration, that, oh, by the way, I've been committing fraud on grant applications for the past 3 or 4 years. He was placed on administrative leave that day. That was Friday. Now, over the weekend, I spammed my friends. Most of my friends are numbers geeks. And I've said, you guys are tired of hearing me yammer on about this because I've been doing it for years. Some of you have talked about writing a letter. Now is politically the best time you will ever have. That Monday, a letter from a whole bunch of biostatisticians landed on the desk of Harold Varmus, the brand new head of the NCI, saying, would you please resuspend these trials and get them evaluated by an independent third body. Varmus called Duke. He said, you're going to suspend these trials, aren't you? They said, yes. He called the Institute of Medicine, said, would you act as an impartial observer? They said, yes, it's stinky enough, we'll do it. And before they got to that, however, they said, we'll start in December. In October, Joan Evans, the senior author on most of these papers, sent a letter around to a bunch of authors saying, you know what, we may have to pull one of the papers. What paper would they have to pull? The one dealing with cisplatin and pemetrexed. Why were they going to have to pull it? Because on a closer examination of their database, it appeared that 43 samples were mislabeled and they could not match the other 16. Which is what we told them the previous November before they enrolled more patients in the trials. Shortly thereafter, Duke officially terminated all of the clinical trials in question and announced that in retrospect, these clinical trials should never have been run. Bodhi resigned, and the cascade began. There were lawsuits filed. There were retractions, about a dozen, which is not enough to make the retraction watch leaderboard, so I don't feel deprived somewhere. But the FDA went to Duke and said, reassure us that you know how to treat patients. It hit the front page of the New York Times. It hit 60 Minutes. It hit all these fun things. So, a few cautions about it. This story is pathological. This is a bad story. Most things don't happen. You don't see these many mistakes in Cascade. It doesn't happen at all. But I will tell you that working at MD Anderson, I recognized each and every one of them because individual types of mistakes I'd seen in other data sets that came to me at MD Anderson. I've seen confounding in the experimental design, running all one group in one day and all the other group a few months later. I've seen mix-ups in sample labels. I've seen mix-up in gene labels. Most of the time, because it comes to me before publication, I say, this is a mix-up, send me the raw data, I'll work with it. But what I know as a result of that is the most common mistakes are simple. But let's say you make a mistake, and you don't have a statistician who catches it. And you publish, and you say, well, there's not enough room in the journal. We don't need to actually publish the raw data. Let's just publish the summaries. At which case, trying to figure out that there was a mistake and what that mistake was just became a hell of a lot harder. Now, I include this slide for people who haven't seen Lee's talk the previous hour, which is that I told you about one group. Now, that was bad. But it doesn't necessarily mean there's a pervasive problem. But what came out is that due to a coincidence of timing, we came out with a thing saying, by God, this is how bad it can get. And Lee came out right around the same time and saying, by God, this is widespread. Folks started listening. And as a result of that, a few things happened. So lots of money being wasted. So where was the money going? Well, let's see. What were the types of scripts that people were making most often? That bit, biological reagents and reference materials, that's did you get the labels right? Study design, did you avoid confounding? Data analysis and reporting, did you actually supply the code? 90% of $28 wasted billion can be avoided if you think about it before you run the experiments. So we were asked what we would recommend. And here's a neat trick, which is I took a team of statisticians, about 50 of us, we wrote a report for Nature saying, here's what we suggest. Nature got back to us and said, the author list is too long, we're not going to list everybody. So actually what happens is that paper is listed as a single author publication by Keith Baggerly, and there's an appendix listing all the other authors. So that's how I have a single author publication in Nature. Cool. The fun thing is, we said, what types of things do we need in a publication at the time of publication? Well, basically, we now need the data, and we need the code, because written descriptions no longer cut it. But more to the point, what do we want? Oh, start listening. Will you play? No volume. Okay, but this will not work as well because I am not Brian May. But I want it all. I want it all. I want it all. And I want it now. That's what Queen said. We'll steal their phrasing because we can't better it. And in this case, at the time of publication is when the journals have leverage. That's when we want to insist upon saying, you've said that you can do this, commit to us and submit data at this time saying, we can prove it. And actually, one of the things that we've seen is that a few others have taken up this thing. And actually, one reason that some of you may be here is that there's a lag time between institutions taking up these reviews. The NCI took up some of these guidelines in 2013. The NIH officially took these up for grant application as of January of this year. So it takes a while. And some of the things the NCI asked for are NIH now. Do you know what cell lines you're working with? Do you know what the samples are? Have you avoided confounding? Have you told us what you did? It doesn't need to be super complex. By the way, all these slides will be posted online in the next few days. You can download them all, and if you have questions about that or code or anything like that, you can send me an email. That works. And I'll tell you, this isn't impossible because we've been doing it for a good while. But have we solved the problem? I was just trying to think about how to answer this, and then Science ran this story last week, where they went and they looked at a whole bunch of papers, and actually, this is a news article, so bring on some of their science writers, and there's a paper under review now. This is results from a pre-pub stuff, a reprint, not peer review, but what they did was they looked at 5,000 papers and they looked for problem signs of data falsification or fudging or plagiarism, etc. And the authors found that of the 5,000 they looked at,
A whole bunch had problems, about 30% had problems overall. The rate was 34% in neuroscience, 24% in medicine, and one of the reasons these rates are so high is because a whole bunch of the problems are showing up in paper mills / predatory journals, and they're being aided and abetted by ChatGPT, AI, the ability to generate plausible-looking phrasing automatically. And the journals are only now beginning to fight back with their own AI tools for detecting fudging plagiarism and things like that. So it's still an issue, folks. And if you really want to keep up on this and learn from this, one recommendation I will echo here is I say, go to Retraction Watch, read them, they're often fun, and in a perverse sort of way, sometimes depressing. But one reason we like Retraction Watch is that this was the very first story they were not doing anything stupid, sorry, that was an old one. But the very first story was, we're gonna talk about retractions, we expect it will be done in 2 or 3 months, but we thought there was a noisy story we should tell you about. And this noisy story was this story about some folks at Duke who were running clinical trials. We have a soft spot with them. So that's the story I've been telling. Now, I will also wind up by telling you that actually, I'm an optimist, and the reason I'm an optimist is that while I've told you about all these problems, I've also been watching the quality of data and papers that have reached me over the past 20 years. The quality has been monotonically increasing, subject to slight variation. So we've gotten better. We've gotten better about reporting code. Some journals have gotten better about asking for it. In the statistics literature, they've gotten better about having not just referees, but associate editors at journals who do nothing but check the code in papers that have been supplied to say, does it produce the results? So we're making progress. We're getting better, and we improve it. So that's good. And the story hasn't stopped. So I could go on for a long time. I have promised the organizers of this conference I won't. So, but I do have to acknowledge that, by the way, this thing, the story that I've told you, it took a bit longer than an hour to put this together. Kevin Coombs and I, Kevin is first name equals, estimated that, point estimate, ballpark, reverse engineering all this took us a bit over 2,000 man hours. That's more time than you should have to spend on analyses that have already been done. That's also a reason that this particular type of approach does not scale. And that's a reason we need to be doing something else to not rely upon it. And the last thing I have to do is I have to acknowledge one last group, which is you guys for putting up with me for the past 45 minutes, because that's what I've got. Thank you for